the number of all possible values of theta, where theta is between 0 and pi, for which the system of equations, y plus z cosine of 3 theta plus xyz sine of 3 theta, x sine of 3 theta is equal to 2 cosine of 3 theta over y plus 2 sine of 3 theta over z. xyz sine of 3 theta is equal to y plus 2z cosine of 3 theta plus y sine of 3 theta has a solution. X naught, y naught, z naught with y naught, z naught not equaling 0 is, which just means either of these cannot equal 0. So this is a pretty daunting thing, and I just like to simplify it as much as possible. So what I want to do is, I want to do two things. All of the trig functions here they're taking sine or the cosine of 3 theta, and they have theta between 0 and pi. I want to do a little substitution. This is just for my brain because it simplifies my logic a little bit. Let's make a substitution that u is equal to 3 theta. And then the u, when theta is 0, u is going to be u is still going to be greater than 0. And when theta is pi, u is has to be less than 3 pi. And so this boils down to, let's find the number of u's between 0 and 3 pi, where y plus z cosine of u is equal to xyz sine of u, so on and so forth. So with that, let's do that substitution. And also, I'm going to rearrange these so that they start to at least look a little familiar, and see if we can somehow start manipulating with these equations and actually try to cancel out terms. So this first one up here, just to get into ways that I can recognize, let me distribute the cosine of 3 theta, or which we'll now call the cosine of u. So let me just write this. This is u, this is u, this is u now, this is u, 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 and u. So this, if we distribute the cosine of u, this becomes cosine of u. Let me put the y out front. So it's y cosine of u plus z cosine of u is equal to xyz sine of u. That's this first equation. This second equation, it looks like, well, if we multiply both sides of this equation by yz, we're going to have an xyz sine of u on the right-hand side, which is the exact same thing we have here. So let's multiply both sides of this equation by xyz, both sides. The right hand of the equation, not by xyz, just by yz. So we're going to multiply both sides of this equation by yz, so that these leave the denominator. So we're also going to multiply the right side by yz. The left-hand side becomes xyz sine of u. And let me write it over here, just right under this. So this is xyz sine of u. And then yz times 2 cosine of u is going to be 2z cosine of u. So 2z cosine of u. I just swapped the sides. And then yz times 2 sine of u is going to be 2y sine of u. So 2y sine of u. So this is the second equation. And now they don't look that different. When they're written like this, they look very different. Now let's think about this one. This has an xyz sine of u. I'll do it in magenta, this equation. xyz sine of u, I'll write it on this side. xyz sine of u is equal to, let's see, we have a 2z. Let's distribute this cosine of u. We have a 2z cosine of u. So plus 2z cosine of u plus y cosine of u. So we have a plus y cosine of u. That's that times that, plus y sine of u. So let me scroll to the right a little, left a little bit. Y sine of u. So I've rewritten these three equations. The problem looks a lot less daunting right now. And let's try to figure out the number of u's between 0 and 3 pi that will satisfy, that will give us a solution here. So let's see. All of these three equations are equal to this expression right over here. So the left-hand sides of these equations all have to equal each other, because they all equal the exact same value. So let's do that. Let's see what we can do in the way of canceling things out. Let's see if we use, let me this is a plus right here. I don't know why I wrote an equal here. So let's see. If we write, this has got to be equal to that. So let me use these two first. So this thing, so we have 2y sine of u plus 2z cosine of u is equal to this, which is that, which has to be equal to this, is going to be equal to y sine of u plus y cosine of u plus 2z cosine plus 2z cosine of u. We have 2z cosine of u on both sides, so that gets rid of the z terms. And then we have 2y sine of u, and we have a y sine of u. So if we subtract y sine of u from both sides, we end up with a y sine of u, just subtracting this from both sides. 2y minus y sine of u is just going to be y sine of u, is equal to y cosine of u. So in order to have a solution here, in order for this to be a sensical statement, and remember y cannot be equal to 0. In order for this to end up having a solution, the coefficients on y have to equal each other. Sine of u has to be equal to cosine of u. So that's one constraint. Sine of u has to be equal to cosine of u. And let's just think about the unit circle and think about how many times are the sine and the cosine equal to each other when you're going between 0 and 3 pi. So I got the unit circle right over here. Now, clearly, when we're at 45 degrees, sine and cosine are equal to each other, or 45 degrees is the same thing as pi over 4. We're at they're equal to each other. You might be tempted to do this over here, but here the cosine is negative, sine is positive, so that won't work. They're both negative over here, but they're equal, so that's another value. And then this won't work. So far we've traveled 2 pi. We can go another half. We can go 3 pi. So we can go back to this one again. So we can go back to this value again. So there are 1, 2, and then when you go all the way around again, 3 values. And then we can't go back to this one because we can only go, let me do this in another color. We can only go 3 pi for u. So we can only go, that's 2 pi, and then go another time around. That is 3 pi. So there's 1, 2, 3 values. So there's three possible u's just from this constraint, just when we used this blue equation and this magenta equation. Now let's just make sure that there aren't any further constraints over here. So let's see if we can, let's use 2 of the other equations. And the ones that I would want to use, that it seems like there might be some cancellation. Well, we could use either this guy and this guy. Y cosine of u plus 2z. Yeah, why not? So let's use, so as long as we're using all 3 equations in our constraints, we will have kind of properly constrained all of the possible solutions. And so let's think about it. This equals that, which is equal to that, which is equal to that. So we could write y cosine of u plus z cosine of u is equal to this whole thing over here, is equal to y sine of u plus y cosine of u plus 2z cosine of u. And then we have a y cosine of u on both sides. Those will cancel out. We can subtract a z cosine of u from both sides. And so we would get 0 is equal to y sine of u plus z cosine of u. And this seems like a pretty benign statement. Y sine of u plus z cosine of u is equal to 0. Well, let me make sure. See, y sine of u plus z cosine of u is equal to 0. That means that means that 2 times this is also going to be 0. So this is equal to 2 y sine of u plus 2z cosine of u is equal to 0. And the only reason why I multiplied it by 2 is because then now this looks identical to this. So when I used this equation and this equation, I got a constraint that this expression right over here, essentially needs to be equal to 0. That this expression over here essentially needs to be equal to 0, which is okay. Because u could make the sign equal to 0, or x can be equal to 0. Remember, they didn't put any constraints on x. X can be equal to 0. So this isn't really constraining us. X can clearly be equal to 0, which could make this thing equal to 0. So it's not limiting our constraint. So now we've used all of the information that's in the problem. We've used all three of these surfaces, essentially to find out if there's an what are the constraints we have for an intersection of the three surfaces. And the only real constraint is that the sine of u has to be equal to the cosine of u. And there are three possible u's between 0 and 3 pi that satisfy that.